I'm not a Hertz fellow. I didn't even know this meeting existed until I was invited, and I'm having such a fantastic time participating, listening to wonderful talks, and interacting with all of you who are really so wonderful. You know, sometimes when people ask me, what do I work on, I say, I don't know. Because my research right now is studying a mysterious phenomenon fairly recently discovered called fast radio bursts. And I'm hoping in this talk to share with you the excitement of the field by also including you in decision making about exactly what we're going to talk about here. So this is a little bit like choose your own adventure. At several points in the talk, there'll be a juncture where I'm going to ask you to decide what you want to hear about next. Let me go ahead and advance. Now, you know, when you look at the night sky, you're used to seeing, you know, something very calm. Probably, if you get a little bit out of the village here, you'll see beautiful night sky, beautiful stars that are always there if you come back the next night or in 10,000 years or 100,000 years. It'll be the same thing in the sky, very peaceful. But what I'm talking about today is a transient phenomenon. So it's the time domain astronomy and a great mystery. This has captured the imagination of certainly of the popular press for reasons we'll get into a little bit later. But what do these things consist of? What is a fast radio burst? So these are brief, and by that I mean just milliseconds, bursts of radio waves that are happening all over the sky. The first one was discovered using this telescope here. That's in Australia. You can see the 3-story building there at the bottom. There. And this is something, this is not rare. These are happening all the time. If you could observe the entire radio sky every day, all of it, you would see about 1,000 of these per day. So then this is, you know, happening presumably for billions of years. This is not an uncommon phenomenon in the universe. You might wonder why we only discovered it, you know, fairly recently. It's simply technology. And we don't know what these things are. We do know, and I'll explain this in detail, that they're coming from the well outside our Milky Way galaxy and from cosmological distances. And the last thing I'll say at the moment is that they're not microwave ovens. And I'll say more about that, or I might say more about that later, depending on if you're curious. Now, how do we see these? What do we see when we see one of them? So this is a classic plot of a fast radio burst. On the x-axis is time, and you see that's about half a second of data. On the y-axis is radio frequency. So typically we're in the megahertz, hundreds of megahertz to gigahertz band. This happens to be 1.2 to 1.5 gigahertz. And what you see is that you know, this thing here that's at a fixed radio frequency and that is on, that's a TV station. That's not interesting. In fact, we have a lot of interference, terrestrial interference, that we have to filter out. The signal is this thing that's sweeping through the band. It arrives at high frequencies first and then at low frequencies later. And I'll explain why that is. And in fact, it's exactly that behavior that's telling us that this is coming from a cosmological distance. This came from, this was observed with Parkes. And if you correct for this effect, because we believe at the source all the radio frequencies are being emitted at the same time, if you correct for this dispersive effect, you de-disperse the data. And we do that in software because we digitize both in time. We digitize the signal from the telescope antenna both in time and in frequency. We can, in software, delay the lower frequency so that we bring them all together at the same time, so it would look vertical on this plot. And if we then sum over all radio frequencies, you get the inset here. So what we see at the radio telescope is basically noise, then the burst, and then it goes away and it doesn't come back. So that's what the phenomenon is. So, okay, here's the first juncture. Choose your own adventure. When I say it comes from a cosmological distance, Maybe some people know what I'm talking about, maybe not everybody, so I could first spend a couple of slides explaining what do I mean by cosmological distance, what the scale of the universe. Or I could just get into right away, how do we know FRBs are from cosmological distances? So, show of hands, who would like a little primer about what cosmological means? Okay, let's do that. And then we'll get back to question number 2. So you live in a galaxy. This is not the Milky Way galaxy. It's very hard to take a picture of the outside of your house when you're standing inside it. But we believe our Milky Way galaxy looks a lot like the spiral galaxy. You are approximately here, which is something like 24,000 light years from the center of the galaxy. And so fast radio bursts are not coming from within this galaxy, within our galaxy. They're from far outside. And so what I mean by that, you're probably familiar with that first frame over there. That's planet Earth. If you zoom way out of planet Earth just to the solar system, and if you could see the little red smudge there, that's the previous frame. So the Earth is over here. The scale of the solar system is much larger than the radius of the Earth, obviously. Then you could zoom out where the whole solar system is just a little smudge. That's our interstellar neighborhood, meaning the closest stars, a few light years away. These are now a few light years away. And if you zoom out of the interstellar neighborhood to the scale of the Milky Way galaxy, we're just a little smudge. The whole interstellar neighborhood is just a little smudge, several tens of thousands of light years from the center. And if you zoom out of the Milky Way galaxy to the local galactic group, then actually our galaxy is a bigger smudge on that scale, as is the Andromeda galaxy, which is our nearest large spiral galaxy neighbor. You're talking about something like 2.5 million light years now. And if you zoom way out of there, this whole local galactic group is now just a smudge on scales. Now we're talking hundreds of thousands to millions of light years. That is the local supercluster of galaxies. We see we're just a little smudge. You zoom out of that, the whole supercluster of galaxies is now just a smudge on the scales of millions of light years. And then if you zoom out to the largest scales of the universe where it starts to look homogeneous and isotropic, and we're in the scale of billions of light years, the whole local supercluster is really just a smudge also. And that's the scale from which fast radio bursts are coming. Billions of light years away from the most distant reaches of the universe. So how do we know that? So I mentioned something about dispersion. And you're already familiar with dispersion, so you know that white light is made up of the colors of the rainbow. You can see that if you pass it through a prism. It splits it geometrically, but what you don't realize is it also splits it temporally. That if you could see the time it took for all those colors to come out, they come out different, so that's called dispersion. And you might say, a lot of you are familiar with this, that the different colors are traveling at different speeds, and that seems to violate, equals mc squared, the speed of light. But that's only true in a vacuum, and space is definitely not a vacuum. So space is filled with lots of plasma. You can just see that if you look up at the night sky and you see, in this case, you're seeing a lot of dust that's blocking the center of the galaxy. But in addition to dust, there's plenty of ionized plasma, there's plenty of free electrons, and free electrons are radio waves prisms. So when radio waves travel through free electrons, they get dispersed. And the total amount of dispersion is proportional to the column depth of the electrons. So the more electrons they travel through, the more dispersed it is. And so the picture here is if you have a fast radio burst source, we believe all the radio waves are being emitted at the same time, but travel at different speeds to Earth, and that's the source of dispersion. So here I'll represent different frequencies of radio waves by different colors. You see it's white at the source. But by the time it gets to the Earth, the high frequencies arrive first, and then the low frequencies. And so this is how we know, this is how we know that fast radio bursts are coming from cosmological distances because we know how much plasma there is in our own galaxy. So again, that's not the Milky Way, but we have maps of the distribution of, at least models of the distribution of free electrons in our galaxy. So the bottom plot there is one of our best models for how free electrons are distributed in the galaxy. You can see the spiral arms. It's debatable, it's controversial if there's that sort of hole in the density of free electrons at the center of the galaxy. But what we have is a contour plot. Now it's a three-dimensional contour plot. This is a model that's been calibrated by galactic radio sources like the neutron stars that Caitlin mentioned, radio pulsars within our galaxies show the same dispersive effect but have some of them have independent distance estimates. So from that we can calibrate the distribution of free electrons in our galaxy. And this is the best model. Earth is where the little Pac-Man is at the top. These are the different spiral arms. The galactic center is over here. And so for any direction in the galaxy that you're looking, for a galactic source, we measure the dispersion measure. These are contours of constant dispersion measure. You can know the distance of the source. So you measure that dispersive effect. You know the direction. You look at your model. And this is just a slice. This is a slice through the plane of the galaxy. But you can look in any direction. You know the distance to the source. And in particular, in any direction, there's a maximum. Because the galaxy has its own plasma, its own interstellar medium, its own halo of gas that we know about in plasma. And so in any direction, there's a maximum possible column depth of free electrons. So there's a maximum amount of dispersion you can have. And so getting back to our fast radio burst, in the direction this burst appeared, the maximum from the Milky Way galaxy, we call it the dispersion measure, the DM of the source, in arcane astrophysics units, don't worry about what that means, but was 25. Whereas if you actually measure this amount of dispersion, you quantify that, it's more than 10 times greater than anything our galaxy could explain. And so from that, we immediately knew that it had to be way outside our galaxy. This was jaw-dropping. We had never seen a radio emission of this nature from within our galaxy. And not only that, we know the intergalactic medium free electron density is very tenuous. It's much lower than inside the galaxy. So to accumulate that much column depth of free electrons from the intergalactic medium, it tells you this thing must be really far away. And then that means it must be a very powerful event. So that if we estimate, given what we think about the intergalactic medium, and this has not been observed before. There's models about what the intergalactic medium plasma density is. And they're very relevant to understanding cosmology, the origins of the universe, and how the universe expands. Given those models, we could estimate, and we would estimate in that case that the total energy in this burst had to be somewhere, around 10 to the 34, 10 to the 35 joules. So the Hiroshima bomb was about 10 to the 11. So sometimes astrophysics feels a little esoteric, but I kind of think 10 to the 35 joules, we should probably understand how nature produces these explosions. Okay, choose your own adventure number 2. Would you like to know what microwave ovens have to do with this story? And this will also tell you a little bit about how science works. Or should we just jump to what we think FRBs might be? Microwave ovens, anybody? Okay. So early in the history, it's not that long ago, it was a few years after they were discovered, the people at the Parkes telescope started to see some FRBs that looked a little different from all the other FRBs. So here's an example. The frequency sweeps were a little strange. They still swept through the band in the way that we expect for sources going through interstellar plasma, but they were kind of blobby and they were a little different. And they started observing a few dozens, not quite a few dozens of these, and they one day they were very puzzled, why were there some that were so clean and some that were like this? So they plotted a distribution. The strange events are the light gray, the regular events are the dark gray, and they plotted versus time of day in Australia time. And they noticed that the strange ones were always happening at lunchtime. and what they realized, they had a grad student there was a microwave oven in the kitchen at the Parkes telescope. So if you, again, one more time, with the Parkes telescope, if you steer it in just the right direction toward the center where the kitchen is, and somebody had to be impatient and open the microwave door before it shut off, then it produced a fast radio burst. And so there was a student, open, close, and there was somebody at the telescope, yeah, we saw one. And anyway, here's why I think this is really important, just from a scientific point of view overall. This was published in one of the most prestigious astrophysical journals. You could see it here. Subsequent tests revealed that they called it a periton at the time, was a funny name for it, but it can be generated when a microwave door is open prematurely and the telescope is pointed in just the right direction. And they published this. You know, we are proud of our mistakes, and we're proud of understanding our mistakes. And but really, the exciting thing is that the rest of them, the ones that were not like that, were shown to be distributed evenly in Australian time, as you would expect for a cosmic source. So this really lent a lot of credence to these things being real. And at that time, you know, suddenly the theorists went wild, and there were more papers in the literature than there were events, but on lots of different ideas. An exploding star, like a supernova, could be neutron stars colliding, or a neutron star colliding with a black hole, or comets and asteroids. And every one of these bullet points, this is a quantitative theoretical paper that was in the literature, and I'm only scratching the surface of the ideas that were out there. Evaporating black oscillating primordial cosmic strings. One of the models that today, and I will explain why we believe is a leading model for these, is magnetars, which are ultra highly magnetized neutron stars. And so, choose your own adventure number 3. I could tell you more about magnetars, or we could just jump to a really important question of FRB science, which is, do FRBs come from other galaxies, and what types? You know, there's old galaxies, there's young galaxies, galaxies store. What kind of galaxies do they come from? Both. Okay, great. Okay, so what are magnetars?
Vicky.
Question.
Oh. The box is on.
Okay.
Yes.
Yeah, I was just curious. So it seemed like all of the hypotheses were kind of these like explosions of some big thing colliding with some other big thing. Is there a reason why they center on that? Is there something that like makes people think that it's an explosion? And also, does that mean these explosions are happening in like a millisecond?
Yeah. So absolutely. So it has to be something of tremendous power. It has to be something, at least for the moment, that you see and is gone. And it has to be something, so you said very big things. Those were not big things. Those are all really small things. So it has to last only a millisecond. So it has to be some sort of compact object.
I see.
Yeah, and so that immediately, you need a large source of energy. So a black hole, it's probably gravitational potential energy. If it's a neutron star, there's all sorts of ways to get that kind of energies, but it has to be something small. Neutron star is only 10 kilometers across. So light travel time is very small. So if you want something that is only going to last for a few milliseconds, then you're driven to those kind of models. Okay, so what are magnetars? So these are objects, they've been fairly well studied. In fact, this is what I did for 20 years before I worked on FRBs. They are ultra highly magnetized young neutron stars. The magnetic fields, Caitlin mentioned, 10 to the, I think in Gauss, and I think it's a 10 to the 4 factor, I hope I'm right, 10 to the 11 Tesla, something like that. These magnetic fields, we believe, are unstable within the neutron star. We don't know exactly the physics inside the neutron star to support these enormous magnetic fields, but we do witness fairly ubiquitously massive bursts of X-rays and gamma rays from magnetars. They're very rare in our galaxy. We only know of about 24 of them. And I put a little asterisk to remind myself to say, if you're curious about magnetars, it so happens at McGill, because I used to work on this, we have an online catalog of the couple dozen magnetars in the galaxy, and you can Google magnetar catalog and you'll find that. They have plenty of internal stored energy that if they had some sort of enormous event associated with the huge X-ray and gamma ray bursts that we do observe with X-ray and gamma ray satellites, there'd be more than enough energy to produce a radio burst. But they hadn't been known for their radio bursts. They were known for X-ray and gamma ray bursts. So people scratch their heads a little bit. There's enough energy. It's compact. They are volatile. But I'll get to soon. They were not known until for radio bursts. Now, coming back, another question you could ask is, what kind of galaxies do these come from? So here's the problem. The Parkes radio telescope, it's diffraction limited, meaning its angular resolution on the sky is pretty poor. When you look at the uncertainty region of where the FRB came from, there's 1,000 galaxies it could have come from. Now, if some of you remember your physics, so the lambda over d relation, if you have a larger aperture, you can get better resolution. And so if you go to a larger telescope, like the Arecibo telescope in Puerto Rico, used to be the largest telescope on the planet. But still, that wouldn't do. I mean, you'd have a few dozens of galaxy candidates for the host. You really need a telescope, and I'm going to show you in a minute, like the very large array it pinpoints very well, because it's an interferometer where the telescopes that form part of the interferometer are kilometers apart. And so let me show you what I mean. There's Parkes, 64-meter aperture, very large region on the sky, but that's about the size of the full moon is its uncertainty region. If you go to Arecibo, which of course no longer functions, unfortunately, it's 300-meter aperture. You see there, and I might talk more about Arecibo depending on you guys, or the very large array. There, it's many, in this case, something like 85-foot telescopes. They can be distributed over many kilometers. But the problem with an interferometer, so that's what you want to pinpoint to see if it comes from a galaxy or not, but the problem is the field of view is so small. So with the interferometer, you don't know where to look, because it can only see a tiny region of the sky at once. The FRBs could be happening in different directions. Okay, choose your own adventure number 4. I could tell you more about the beloved Arecibo Observatory, which I loved and which I was heartbroken when it failed. Or we could just jump to what surprising major FRB discovery Arecibo made before it stopped operating. What? Say it louder? Jump. Okay. Okay, sorry, so I let jump. Yeah, I was going to tell you about Jodie Foster. Okay. So what did Arecibo find? First, it found the first non-Parkes FRB, and the Parkes people were so relieved. They were so happy because, was it a flaw in their software, or was it some other weird thing so this was the first non-Parkes FRB, and there you see the classic dispersion sweep and the inset there where you de-disperse. But what was shocking about the Arecibo event was that we kept staring at that part of the sky, because Arecibo, with a larger collecting area, is so much more sensitive, and it repeats. So this was a shocking discovery. We were not expecting this. None of the Parkes FRBs had ever repeated. Here you can see these plots have been we de-dispersed it. They're all at the exact same dispersion measure, and from exactly the same position on the sky. That source is, now it doesn't always do that. And we got lots of press about this. It's very exciting. It's quiet for months, and then burst. Those are 10 bursts in 15 minutes. So immediately, with one observation, that 10-minute observation, we eliminated all the cataclysmic models, at least for this source. You can't have a supernova 10 times in 15 minutes. Like, that makes no sense. So that was a gift. And then the second thing it did was it told us where to point. And so then we could go to the large interferometer, beg for time, and then see nothing, because the source doesn't cooperate. So we worked really hard to get that time, stared, and we saw absolutely nothing. But then we begged for more time at the telescope, and they gave us more. And finally, during a test observation, it exploded. And for arcane reasons, the way we showed the data was where the pinpoint is there. The circles are the Arecibo uncertainty regions on the sky. The pinpoint is what the VLA found. And it's found it with exactly the same dispersion measure that we saw from Arecibo. So we knew it was the same source. And then we started seeing multiple from them. And then we knew exactly where to look. And so we could go with an optical telescope, beg for time there. Hey, guys, and they gave, so we went to the 8-meter Gemini telescope in Hawaii, and we were shocked because we thought it would be coming from a big, nice spiral galaxy like the Milky Way. And no, it's coming from a puny little dwarf galaxy. And the way I'm saying it is exactly how we reacted. There are dwarf galaxies, tiny. Why is that? Turns out it was a red herring. But at the time, it was very puzzling. But the one good thing was we can measure the distances to galaxies very easily using their redshifts. And this one was definitely at a cosmological distance. So if you were worried that, oh, the argument with the dispersion measure was incorrect because maybe there's some cloud in the way or something, no. This was the first direct measurement of a cosmological distance for a fast radio burst. We got lots of press, and here is the famous science writer Dennis Overby calling it ordinary physics. And I want to bring one of those to his house late at night and explode it and see how ordinary he finds it. But meanwhile, the New York Post, like, we never said that. Okay, so choose your own adventure number 5. How do we know FRBs are not aliens? I could answer, they're not. You want to know that, yeah, okay. And then the other option was, what if we never figure out what FRBs are? Then do we care about them? I mean, what if we can never figure this out? Why do we care? So the argument for FRBs not being aliens. So first of all, there's a whole now vast phenomenology that totally looks like natural sources. But I think the most compelling argument for them not being aliens is they're everywhere on the sky. If you had an alien civilization billions of light years over there, it's not talking to an alien civilization over there with the same exact technology. We see them. This is a sky distribution representation of the locations of all the FRBs that we've discovered so far at the CHIME telescope that I'll tell you about shortly. It's all over the sky. And this is just a 2D. This is the projection onto the celestial sphere. They're at vastly different distances. We see them in the local universe. We see them in the distant universe. They're everywhere. There's no way that could be one civilization. But coming back to the question of, what are these useful for besides just curiosities? Here's a couple of really bright fast radio bursts that we got from the CHIME telescope I'm going to tell you about shortly. And you just see there's so much information. When radio waves propagate through plasma, they get imprinted with all sorts of information about the properties of that plasma. And this is unlike, you may have heard of gamma ray bursts. The gamma ray bursts are famous other transient and time domain astrophysics problem, but gamma rays just sail through anything. Radio waves, when they travel through plasma, they get dispersed. They get imprinted with scintillation effects. So this scintillation has to do with the turbulence and the motions of the plasma that it's traveling through. They get scattered. I don't have a plot showing you that, but we can see other types of information about how the radio waves are delayed by some that would have gone over there, getting scattered back to your line of sight. So you see a slight time delay. Only on the length side. They're polarized, so we see Faraday rotation. If you're familiar with Faraday rotation where you have magnetic fields. We can probe magnetic fields of interstellar plasma. And so these things, they're going through, we think of coming from some distant galaxy going to the Milky Way. And what we measure is the sum total of all the electrons along the way. So from the Milky Way interstellar medium, the halo of the galaxy, the intergalactic medium, the IGM, and something presumably from the host galaxy too. But that's not correct, because as these things propagate, they're nicking the halos of many other galaxies. And so you get an additional component from other galaxies' circumgalactic media. But we don't know much about that. We don't know much about the content of the halos of other galaxies, and different cosmological models, different models for the origin evolution of the universe predict different distributions of matter in the universe. So here's one simulation of the so-called cosmic web. This is now looking at the largest scales. If you looked at different simulations, you would see very different statistics of the distribution of matter in that sort of web between all the galaxies. And so this is something that fast radio bursts are a novel probe of. We can, for example, here, this is now, the Australians built a whole new telescope, not just for this purpose, for other purposes also. That's the ASCAP telescope that can find fast radio bursts and localize them on the sky at the same time. Unlike Parkes, it wasn't able to do that. Unfortunately, their field of view is very small, so they can't find many of them. But you could see here some of the fast radio bursts indicated with white circles and some of the galaxies. So here, right away, we knew, some of them are actually in normal galaxies, normal spiral galaxies, not just dwarfs. But by doing that, we can compare the column depth of free electrons with the distances of the galaxies. And so one of the brilliant things in this paper by my Australian colleagues in Nature, showing the prediction, that black line is the prediction of how many free electrons you should have. So this plot shows distance to the galaxy in units of redshift. Don't worry about that. But distance to galaxy, the scale here is something like a few billion light years. And the y-axis is the extragalactic component of the dispersion measure after you subtract off the galactic component. The black line is a model prediction for the distribution of free electrons in the universe. So as you go further out, you get more dispersion measure to the intergalactic medium. And those points are the first few FRBs they started finding. And yes, there's scatter around there, but this was the first observation of the universe's population of free electrons. And it came so close just to nailing being exactly where the model predicted from totally independent observations of cosmological. But you see, there's scatter there. The scatter is probably because some of these FRBs are in host galaxies that have their own interstellar media, contribute their own free electrons. And they have their own halos. There's an interesting problem here. If you could populate this with thousands of them, you're going to map out and see the content and the matter distribution. You could test different models for the matter distribution in the universe. So that's really what you want. You want thousands of them. ASCAP's not going to be able to do that because they can only do a few per year. So you want to find more of these. You want thousands of them. How do you do that? How do you study a phenomenon that's transient, lasts a millisecond, and you don't know where or when it's going to happen? You don't know where to point your telescope. So that's my current choice of adventure. And now I'm going to tell you about the Canadian Hydrogen Intensity Mapping Experiment. And you say, yes, that is a telescope. That's a telescope we're using right now. Now, you see the name of the telescope, Hydrogen Intensity Mapping. It was designed for a totally different purpose, for cosmological mapping of 21 centimeter radiation to study the accelerating expansion of the universe. And I'm not part of that project. I just came along and said, hey guys, you could use this and study FRBs too. So this is in Penticton, British Columbia. It's 4 20-meter by 100-meter cylinders. It's a very large collecting area. You're here in Canada. So the collecting area in Canadian units is about 5 hockey arenas. It has no moving parts, this telescope. The cylinders are all oriented exactly north-south. The sky rotates overhead, so we can only see what's directly overhead, more or less. We operate in the frequency range 400 to 800 megahertz, and along the axis of the, oops, oh, I'm so sorry. Come back. Along the axis of each cylinder are hanging 256 antennas. So a total of 1,024 antennas that are hanging here and looking at the sky. They're all connected via vast numbers of thousands of cables that are going into the world's most powerful correlator, whose input data rate is 13 terabits per second, roughly comparable to the world's cellular network that we're analyzing on site in real time. And those are some of the collaborating institutions. That's the fast radio burst team for scale. You could see us standing on the focal line. The different components, part of the correlator, the F engine, that's a FPGA-based correlator built by my colleague at McGill University, Matt Dobbs, is located under the dish. You can't quite see it. There's a GPU-based portion of the correlator we call the X engine, that's in these shipping containers adjacent. And the FRB instrument, which consists of many CPUs, is in another shipping container. And this whole thing was built by, there was a contractor who built the structure, but the brains of it, the wiring, the antennas, the computing, everything was put together by grad students, postdocs, with very few professional staff. We have a few professional staff, but it's a lean operation. Okay, so choose your own adventure number 6. Why cylinders? Why are cylinders so good for finding fast radio bursts? It turns out they're really good at it. And not really or, we add, how does CHIME harness the power of supercomputing? Okay, cylinders, good. Good. Okay, so a conventional radio telescope, typically a parabolic dish. It sees some region of the sky. In this case, yes, Parkes sees about the full moon. But for transient events, you're going to miss most of them. So you get lucky occasionally. A cylinder, on the other hand, it focuses in only one dimension. The other dimension, you're seeing a huge area of the sky all at once. So huge instantaneous field of view, something like 220 square degrees compared to, half a square degree. But in that, with just the cylinder, if you just had one antenna hanging from the cylinder, you wouldn't know where in that huge rectangle your FRB is. But having the huge field of view compared to the conventional radio telescope, you see you're just going to catch more of these things. You have a much larger field of view. I've got to adjust this slide. It just takes too long. The Earth rotates, we stare up ahead, and we start to catch more FRBs because our field of view is much larger. But now we don't know where if you just had one antenna. So if you had one antenna, one cylinder, you see that full swath on the sky. But if you populate the entire cylinder with many antennas and you combine them interferometrically, then you can form digital beams within the primary beam, we call it. And we can independently search each of these for fast radio bursts. And then if you populate all the antennas, you get some east-west direction information as well. So this is the cartoon. In real life, we have 1,024 digital beams, each looking digitally at an independent position on the sky. So it's like we have 1,024 Parkes telescopes all operating simultaneously 24/7. And that's what makes it so, easy. Well, it's easy, a lot of computing. It comes down to computing. So the signal path here, we have the 4 cylinders, the 13 terabits a second. They get processed by the correlator. Then in radio astronomy, you can do 10 things at once. So it goes to the cosmology 21 centimeter mapping back end, and those guys do what they want with it. But at the same time, we can search for fast radio bursts. The total data rate there is about 142 gigabits a second. And then we also do other things with it. We study galactic radio pulsars. So the detection pipeline here is, this is all, it's just supercomputing. We have the GPUs that are doing the digital beamforming on the sky. They're also buffering raw voltage data for each one of for each one of the antennas that we can on demand dump. So we can't save all this data. This is a trigger experiment. We have L1, we call that's our the FRB search engine. That's the CPUs that first have to remove all the terrestrial garbage. We see so much on the sky. We are searching for fast radio bursts in real time there and buffering data for about 30 seconds. If we catch one, we save the buffer really quickly. And then we have all sorts of logic. We want to filter out galactic sources, do another level with AI of removing more other radio frequency interference, and try and localize things as best we can on the source, and then decide what do we want to do with it. So all this happens in those machines there, and we started observing in about 2018 and made quite a splash. This was the number of FRBs discovered by various telescopes around the world prior to CHIME turning on, and then CHIME turned on. And, as Canadians, you don't like to be like that, like, sorry. Sorry, not sorry. And so this is a more up-to-date plot where you can see the largely due to ASCAP, but also Caltech has developed a telescope that's quite similar. They are able to find some and localize them at the same time. That's the white curve. But you see it's a log scale there. They'll find dozens. We're finding thousands. And so this is what it's like to be on the CHIME team. We can we've published one major catalog of 500 sources with in-depth analysis, sky distributions, correlating with galaxy distributions, looking at morphology, statistics, dispersion measure distributions, all of these things. We're now working on our second catalog of 5,000 sources. And by the way, we also put out real-time alerts. And so if you want to get on your cell phone a little message about every time we find an FRB, you could sign up there. I'm sure you all want to do that. Okay, so choose your own adventure number 7. I can show you how we see the sky. So it's sort of an interesting thing. Or I could jump right to what important discoveries has CHIME made. Louder. Let's see, show of hands. You want to see a visualization of the CHIME sky in FRB land? Okay, I'll take it. Yes. Okay, so this is I think this is a super cool plot. This is time on the x-axis. So in this case, it's a few hours, UTC time on the x-axis. And this is now north-south beam. So remember, these cylinders are oriented north-south, and the sky is drifting overhead. And so here we've just collapsed the east-west beams. So you have 256 north-south beams. Okay, 256 north-south beams. And these little horizontal lines, that's something that's a fixed north-south direction. So we call that declination in astronomy. And lasting for a few minutes as it transits through the telescope. Those are galactic radio pulsars. Those little horizontal lines are all galactic radio pulsars drifting through our beams as the Earth rotates. The vertical lines that are marked with RFI, those are airplanes. That's frustrating. It was actually a summer undergraduate. When we first turned it on, we didn't know what those things are. We don't fully understand because they're quite broadband. So we see them from 400 to 800 megahertz. If there was some sort of communications, it would probably be narrowband. We think it could be reflection of just radio noise from cities off the airplane. We're not 100% sure, but the timing of them is exactly with the Penticton airport. I'll just say one last thing about this plot. If you see that big arc, that's what your eye is probably drawn to. The big arc, that is one of the brightest radio pulsars in the sky. And my grad students came to me and they said, hey, Vicki, we could see pulsar 0329 plus 54 for like 4 hours around transit. The thing is only supposed to be in the beam here. If you could see it for 4 hours, I was like, that's really cool. That's not so cool. What it means is we have huge side lobes. That is, the telescope is most sensitive directly overhead, but it can see really bright sources all over the sky. Now that's bad because you want to know where your source is if you want to try and follow it up and see what else is there. You want to know the sky location, but it's good because what it means is in addition to just that 220 square degrees, we have thousands of square degrees of lower sensitivity detector for rare events. So if there's some really honking bright thing, and I'm about to show you, we found one of those. We're very lucky we had those side lobes. So some of the big interesting discoveries CHIME has made, I mentioned when CHIME turned on, there was that one repeating source that we knew of from Arecibo. They're all over the sky. So it turns out there's many repeating sources. We've already published 50. We're sitting on another 50. That's out of thousands. So it's rare. Most FRBs do not repeat, or I should say have not repeated yet. Maybe they're all repeaters. You just have to wait. We don't know. One of the other interesting discoveries as we've now opened up and studied all these different repeating sources is that the repeaters seem to have slightly different phenomenology than the non-repeaters. So the repeaters tend to be a little broader. They tend to last 5 to 10 milliseconds, whereas the non-repeaters typically narrower. And by the way, some of them have microstructures. So when I mentioned we can buffer the raw voltage data and then beamform digitally offline afterward, we can then produce the same time series with much higher time resolution. And we see some of them have microstructures. So currently we're hoping to upgrade this to open up the microsecond sky, something I'm trying to get funding for. Really, you just have to change the computers. The computers are 5 years old. We could do this tomorrow with not much funding. But in any case, the repeaters, they last longer. They have different spectra. You can see these are all examples of de-dispersed repeaters. You see they're much blobbier. The regular ones that don't repeat, they're all broadband. The repeaters have these weird features. They're strange. So could it be different classes? Could it be there's many things in the universe that can produce these huge radio bursts? Some repeat, some are cataclysmic. One of our repeaters is periodic. So one of our repeaters only repeats every 16 days, like clockwork. So this is a plot, it's a little complicated, but it's showing you on the x-axis is year that we've been monitoring, and this has persisted, so I should really update this plot. And the y-axis, this is exposure to that position on the sky. So the beam where we detect, of the 1,024 beams, it's always in the same beam as it transits. And the red line, the red triangles are where we see bursts. And you see they're always some multiple of 16 days apart. We don't, and this was just showing the sensitivity of the telescope is constant. And so we don't know why. To me, it smells like some sort of orbit, but we really don't know why. I'm just going to skip this. I'll just jump to our biggest discovery. I mentioned magnetars, so I wouldn't have been so confident about the model, except that in 2020, just at the start of the lockdown, actually, our telescope operates autonomously, so we could all, from our own bedrooms, could be operating CHIME and looking at its output. And we detected one of the brightest bursts that we have seen so far. It was a double burst actually, and it had this unusual frequency structure which is characteristic of it being in a side lobe of the telescope. We were able to localize it using the raw voltage data. Using a model, I should say, it's complicated, but we were able to localize it on the sky. And given the dispersion measure, we knew it was inside the galaxy. And at the same time, X-ray telescopes were telling us this one magnetar was incredibly active, emitting lots of X-ray bursts. So at the same time as one of those X-ray bursts, this radio burst came from that direction at this dispersion measure. We know that it was a Milky Way magnetar that produced this giant burst. And that we got recognized as one of the top 10 science results in 2020. There we are. That's the magnetar. We weren't number one. Number one was the COVID vaccine. And to that I say, fair enough. Okay, so this is your last choose your own adventure. Are all FRBs magnetars? You might conclude that. We saw one in our galaxy make this giant burst. I should have said this. If you took the luminosity, if you took that galactic magnetar and you put it in a nearby galaxy, it would look exactly like an FRB. It has to be a nearby galaxy. We wouldn't have seen it if it was at a cosmological distance. It was too faint. So are they all magnetars? And I'll tell you the answer, but I could show you the plot that explains it in a little more detail. We don't know. We know some are almost certainly magnetars, but we certainly don't think all of them are magnetars, even most of them. Yeah, question?
Yeah. So I have a silly hypothesis that I want to get your take on. So could this repeating structure be explained by the wave being sort of directional and attached to some rotating object? Right, like if it's every 16 days, maybe it's like a lighthouse going.
Yes. Well, okay. So that is like the magnetar or the neutron star model. So so great question. It's been discussed. We don't know of any neutron stars that rotate on their own axis every 16 days and still have what it takes to produce the beams. We see galactic radio pulsars all the time. Caitlin mentioned, we see some spinning thousands of times a second. The typical one spins once or twice a second. The slowest one we have seen is a few minutes. So to get to 16 days, we don't know how we would produce such an object. And moreover, if you did at such a leisurely rate, the ways that we do particle acceleration in the magnetospheres of the stars require a rapid rotation. It's very hard to imagine how you could do that. But but otherwise we don't know. So another one is precession. Yeah, I mean, if it's rotating and precessing, then maybe, but it's very hard to maintain precession period for many, many years. It should be damped out. Orbit's possible, but there's reasons why it's probably not an orbit. I don't know. There's reasons why it's hard to reconcile with it being an orbit.
Is every burst 10 to the 35 joules?
Yeah. So thank you. So now, that's exactly answered by this plot. So, distance is on the x-axis here. So, sorry, it's in parsecs. Just multiply by 3 to get it in light years. And on the y-axis is the fluence. That is how much energy detected at Earth that we've seen. So at low distances, so this is within the galaxy, right? This is small distances, and these are typical radio pulsars. These are radio pulsars. That's what we observe usually since the 1960s with radio telescopes. There are some galactic magnetars that have produced brighter bursts. This is the range. Now, this is the domain of the FRBs, very large distances, so we're now at billions of light years. They're big rectangles because we don't really know the distance very well to these things unless they're localized to a host galaxy where we can measure the redshift. These diagonal lines are lines of constant energy in ergs. So you have to subtract 7 from the exponent to get it in joules. And so the burst we detect is way up here. So it's at low distance in the galaxy, but huge, huge energy. But the energy of it still just nicks the bottom of the range for FRBs. These, if you can't read it, these are intervals of 10 to the 3 ergs. So this is 1 million times. This is 1 billion. So, as you get out here, the things that we have observed from FRBs are, millions to billions of times more luminous than even this spectacular burst that, won us all the accolades. So yeah, it could be the least energetic ones. And so you were asking about the energy scale. So yeah, so I said 10 to the 35. 10 to the 35 is about here. So that it's even higher than that, really.
So the one that repeats every 16 days. Each of those bursts.
That's a really good question. No, it's not. That one's not quite 10 to the 35, but it's probably 10 to the 33, something like that. Still big. Yeah, that one's 150 megaparsecs away, so I have to do the math in my head, but it's probably 10 to the 33, 10 to the 34 joules. Yeah. Okay, so how are we going to we want to, A, figure out what they are. We want to see what kinds of galaxies they are, but we need big numbers. It turns out the diversity in galaxies, some are in dwarfs, some are in young galaxies, some are in old galaxies. We want to find thousands of them, identify their host galaxies, and measure the redshifts to every galaxy so we can use FRBs. We not only want to understand them, we want to use them to map out the matter distribution of the universe and study how matter agglomerates around galaxies. So what we want to do, and what we're doing, thanks to the Gordon and Betty Moore Foundation, is in addition to CHIME itself, which is located in British Columbia, we're building 3 outrigger telescopes. And our plan is to do very long baseline interferometry on every CHIME fast radio burst and identify galaxies for each of them, and for nearby ones, the location within the host to see, is it in a star-forming region, is it in the center of the galaxy, is it on the outskirts? We're going to do all this. It's in commissioning. This is the first outrigger that we built in British Columbia, about 100 kilometers away. You can see that's a little trolley that you can climb in and wheel yourself around to fix any of the antennas. And we built one in West Virginia. Now we had to roll the cylinder so that it's pointed at the same part of the sky that CHIME on the West Coast is observing. And these are the students who just finished wiring it all up. They were very proud of themselves and very excited. And yes, they wheeled, you can't see the trolley here, but they got to fly around in that trolley. And we're building a third one right now in California. It's been a little bit delayed for complicated reasons, but there you can see the workers are putting the panels on, and we hope to have this thing fully operational by the end of the year. This is at Hat Creek at the site owned by the SETI Institute. Okay, so summary of your FRB adventure. These are mysterious sources. Some of them repeat. So it's only about 3% repeats. Some are probably magnetars, but it's unclear what most of them are still. We've built a novel digital radio telescope that we can use to find thousands of these, and we hope to now basically invent very long baseline synoptic, we call it synoptic interferometry, where you can do this kind of interferometry on these short events where you don't know where they're going to occur. And we hope to unlock the fantastic ability of these sources to be probes of the matter distribution of the universe. And I invite you to stay tuned as we commission our outriggers. You'll hear more from us. Thank you.
Mic runner.
Is this,
oh my God.
Is this mine, by any chance?
We've got a question back here.
Oh, this is fancy. What do you think they are? Down here, down here.
What do I think they are?
Right.
Well, so like I said, I'm sure some are magnetars, but I'm not convinced they all are. And I didn't, so like in the amount of time I had, I didn't get to tell you all of our discoveries, obviously. So some of them are in star-forming regions. We know this because we get the Hubble Space Telescope to point at the distant galaxy, and you can see, oh, it's in a star formation region. That suggests it's a very young object. Magnetars are very young. Magnetars are hundreds, thousands at most years old. But we found one object, one FRB. It turns out it's in an object called a globular cluster, which is a cluster of very old objects. There's no magnetars in globular clusters ever, unless you're going to invent some way. And there are papers in the literature now saying you can produce magnetars by colliding stars rather than core collapse supernova. I don't get too technical, but there's lots of evidence that they're different classes. So what are they? I think the one in the globular cluster, it could be hyper fast rotating neutron star also. With a very powerful magnetic field. If that's true, it's testable. Number one, it should slow down. So in a decade, it shouldn't be as obvious as it is now. And number two, we should eventually see a periodicity on very short time scales. So if we collect thousands of events and do a big Fourier transform on this, we should see a periodicity. One of the discoveries I didn't get a chance to show you, I wanted to, is that we have one FRB that shows, it's not a repeater though, of course. But in that one burst we saw it has 9 peaks. And the 9 peaks are exactly equispaced by 212 milliseconds. So that seems like we caught maybe a rotating neutron star maybe it was gravitationally lensed for a moment, or maybe some weather happened on it. I don't know why. We keep hoping it repeats and we see that same period. That would be so cool. So I think it's some form of neutron star. That's basically, but on steroids.
I sort of meant what's happening on the magnetar that's breaking FRB.
Ah, yeah, what's the emission mechanism? Yeah. So, okay, in conventional radio pulsars, you have this rapidly rotating magnetic field, which means you have a huge induced electric field. That electric field accelerates, rips particles off the surface. The forces there, I mean, you have powerful gravity at the neutron star, 1.4 solar masses, in 10 kilometers, but it's the magnetic and the electric forces that greatly dominate dynamics in the magnetosphere. You get particles ripped, you get acceleration, synchrotron emission in the magnetospheres, and that's just to get conventional galactic radio pulsars. Now you want to amplify that by, and that isn't even very well understood, to be honest. I mean, there's probably some people would argue, but they can do pretty good jobs in magnetohydrodynamic simulations of regular 10 to the 12 Gauss field neutron stars. But you want to amplify that by 1 billion times, more than 1 billion times, compared to those sources. We don't know how to do that. So I would love, maybe we could have a session where we discuss how to do that. That's probably a harder problem than climate change. I don't know. It's tough.
Given the distances that we're talking about, these are presumably fairly much younger in the age of the universe. What kind of signature do you think you'd expect to see locally if these phenomena were happening billions of years ago? What kind of residual signature might you find close to home?
Yeah, it's a very important point that when we look at the cosmos, we are looking in history. But the James Webb Space Telescope, one of the shocking results from James Webb is that says galaxies forming, very surprisingly early, or at least it was a little controversial. I'm not sure the stats, but you find galaxies and stars very, very early on in the history of the universe. So at the distances that CHIME is sensitive to, for aficionados, we can see, out to redshift 1 or 2, which is a few billion light years. There's lots of stars. The stars at that time are not radically different from the stars that we see in the local universe. So what you might see is for an enhanced rate. So you probably, and given the diversity of the phenomenology among FRBs, I don't think you're going to see, and we don't see any sign of, say, an evolving emission mechanism for the production of radio waves. What we might eventually see, and that's what the outriggers, one of the things that you've hit it a little bit, that one of the things we hope the outriggers will show us is the evolving rate of FRBs as a function of distance. So if there were more FRB producing stars in the early universe, that we might be able to tell eventually.
Hi, Vicki. This is a question that you asked us to ask. What did this all cost?
Yeah. Aren't you curious how much it cost to build CHIME? Yeah. So if you sum it all up, it's about $20 million. 20 million Canadian dollars. Yes. So we operate on quite a shoestring. Like I said, we don't have a lot of professional staff. That is a great stress. It's a source of great stress. But we were able to do this. Then to build the outriggers, We went to the Gordon and Betty Moore Foundation. They gave us about $10 million US dollars. Those are such nice dollars. So that's about the scale of this. So, I think, for astronomy, that it doesn't get much cheaper than that. And yet, you can do, if you get lucky with an interesting problem at the right time. And you have fantastic computers at low cost. So because GPUs are cheap, we use off-the-shelf components.
Well, thanks for such a great talk. My question comes from the beginning of your talk when you showed the simulation of zooming out from our solar system all the way to the superclusters into the whole universe. I've always been astonished with the ability that we know that. And that's kind of where my question comes from, is how the astrophysics community has such command and resolution of what we know to be the universe. I always think of the universe as the Laguna Beach, a sandy beach of a bunch of sand everywhere, and we're a tiny bacteria just sitting in the sand, and that little bacteria can't see 5 feet around it, let alone a half a mile down the beach. So is it really just the amazing technology of all of our satellites on the Earth that allows us to have such resolution of this huge universe we're in?
Yeah, so it's both ground-based telescopes. I mean, the ground-based telescopes can, it's true the Earth's atmosphere bothers them a little bit, but to see distant objects, we have very clever adaptive optics techniques where you use laser guide stars. You put a laser in, you observe the effect on the laser and correct the atmosphere in real time to achieve near diffraction limited imaging of the sky. Of course, if you put space telescopes in, then you avoid the atmospheric problem. But you can't put a big, so a Hubble Space Telescope's, 2.5 meters or something. It's not that big a telescope because it's hard to launch, your 10-meter telescope. So we have just a vast array of technologies that's been brought to the field. And you're right, it's sometimes humbling to look out there. But the truth is, as an astrophysicist, when you just do it every day, you get used to these distances. You don't really think about it anymore. I say a megaparsec, which is 3 billion light years. That's pretty close. So the human scale, it's a very unusual scale in the universe. We're just used to it, but the real universe is much bigger than us.
If you, after this question, we're going to have a coffee break. So if you have more questions for Vicki, you can come and find her at the coffee break. But so yeah, whoever has the catch box has the last question.
Anne.
Just
What's
kidding.
your question, Anne?
Ready? Are you ready? Are you ready?
An excellent talk.
Thank you.
I'm wondering how next generation gravitational wave observatories might inform our understanding of what these FRBs are.
Yeah, so we work with LIGO. We would love to detect simultaneous events. I think most of LIGO events involve double black hole mergers, which are not producing any radio waves, unfortunately. What we'd love to see is either neutron star black hole merger, double neutron star merger from LIGO, but there haven't been very many of those. LIGO doesn't localize on the sky very well. So we would be relying on the temporal coincidence, and we're aware of this. So we have the LIGO team has looked through our published catalog. We've also supplied them with our unpublished data and even our below trigger data. So we trigger only we buffer data and save it only above some certain signal to noise ratio. But we can send them metadata about lower trigger where we didn't save the data, but we have some information. They have not found any coincidences. There was one team that noticed a temporal coincidence between a LIGO event and one of our FRBs, and they actually did publish it, but we don't believe that the chance occurrence is too high. It's not even 2 sigma. So I think there's great promise there. We would love to find a coincidence, but so far there hasn't been one.